Why does the sky turn green during severe weather? That's what we're going to talk about today. Hi, this is Jill from the North Woods, talking about nature right outside your front door. Well, if you lived up here in the North Woods, you would understand the weather has been crazy. We have had tornadoes and we've had hail and a lot of really bad weather. And so when we've been talking about how we use spectrometry, it's a fancy word by looking at how color emits out of a thing so that we can understand its properties a little bit better. We talked about it when it comes to everyday life, your fireplace, my dad's oil analysis, how we know what's going on with the planets, and why do lakes and ponds look different kinds of colors of blue. But now let's go ahead and take our learning that we've learned in the past few episodes and talk about the weather. Why is it that light looks so differently when we have different kinds of weather? You might think the light looks wrong. Maybe it's just not exactly what you expected, or a cloud looks like it's not supposed to look. And sometimes it looks dark outside, even though there is plenty of light around. The sun's out and it's still shining, but maybe it's the wrong color, the color that you didn't expect. And so it's almost like the world's been put under kind of a weird filter. My friend and I were out bird watching the last couple of days, and it starts out sunny and then it goes into this weird dark cloudiness. And we're like, what's going on here? Are we about to have a storm? Because it wasn't supposed to be stormy. And so what it is how do we look at the colors around us and understand a little bit about it? Or even take on, like I mentioned before, that when you have really severe weather, there's sort of a sickening green-yellow cast in the sky. The shadows are all off. The grass looks too vivid and saturated. And it looks like all the colors, like on your TV, just got turned up the wrong way. But that means if you live in tornado country, that light means something bad is about to happen. Weather has color. A blue morning sky, a green lit supercell in the afternoon. It not only looks different to us, it sort of has physical differences to us. Like I said, we see the big, beautiful sky, gorgeous day out. But when you see the sickening green of a tornado day, you're like, ooh, that is not good. But basically, everything, all these kinds of weathers are physically and chemically different. The light reaches our eyes have been filtered in a way that's going to tell us a little bit about the story about what's going on. We spent, like I said, these 3 series looking at how light and spectrometry, the science of reading light, reveals the composition of the nature around us. And this is going to be the closest one to home, because when we're looking up at the sky, it's showing us the most visible spectrometry we have that you'll ever encounter. Every color in the sky gives us information about the light that is what the light's going through, and some of these colors have certain kinds of warnings to it. So first of all, if you start out with a blue sky, right? That's the baseline. Beautiful blue sky, a clear, ordinary day. And the reason to understanding exactly why it's like that is that the atmosphere is full of gas molecules. And it's mostly nitrogen and oxygen. It's what we breathe. And then the sunlight travels through them. Remember our sun being a yellow sun, right? It sends its light out to us. And when it travels through these molecules, it interacts with the light itself. And it doesn't then leave the light intact in all wavelengths equally. The process is a scattering, named for a British physicist, Lord Rayleigh, who worked out the math in the 19th century, that basically small particles scatter what we call short wavelengths. That's going to be the blue lights, short wavelengths. So they get scattered, and it causes that light to scatter, which makes it 4 times more strongly perceived by us than the long wavelengths of red. Red has very long wavelengths, and it doesn't scatter. So we see the blue 4 times more strongly. So when we look at the blue sky, even though we have a yellow sun, essentially the blue bounces all around us in every direction, and it just fills the sky with blue. while the red and orange light travels through a more direct, less scattering path. And so when you look at the sky away from the sun, you're just seeing the scattered blue, the light that's being knocked sideways and everywhere, bouncing around in all these molecules, the light that's directed towards your eyes. It's also worth noting, too, that violet light has an even shorter wavelength. Think about that as that, purple way at the end. But our eyes are not sensitive to ultraviolet and to violet. Our eyes are more built around blue. And so the blue becomes more apparent to us because our eyes are prepared physiologically to accept blue more. So even though there is violet in the atmosphere and it's absorbed in the upper atmosphere, the results are that the sky is blue, not violet. And because our eyes favor blue, essentially we see even less violet than even would technically exist. I don't know if you understand. So scattered blue is the baseline of our sky. Everything else, every other color that changes the sky is a departure from that. And each departure has its own separate cause. So think about it this way, that if you are looking at sunsets, for example, so when the sun is directly overhead, its light takes a relatively short, straight path through our atmosphere before reaching us and our eyeballs. And it passes through this modest amount of air. And like I said, the blue scatters, the sky is blue, and the sun, even itself, is yellow-white. But as the sun sinks towards the horizon, it's now setting, the geometry of it all changes. The light goes from a low path, right? We're now, it's on the horizon. It's about to set over the edge of the earth, right? And now it has a much longer diagonal path to reach our eyeballs. And so when it does that, it's basically more than 30 minutes of path length more than it takes us when the sun is directly overhead. So meaning that a beam of light flies off the sun, it takes 30 more minutes to reach our eyeballs than when it's overhead. So that means there's 30 times more gas molecules to scatter the light against it. And when that 30 times more light atmosphere gets in the way, the blue light is already most aggressively scattered, gets scattered away entirely. And so it bounces off to the side. It diffuses and disperses before it even reaches you. The green light, we're going in the color of the rainbows, right? Goes next. So what survives? The red and orange. We've learned about this when we talked about the lakes, that sometimes when you see a green lake, we talked about the depth, that essentially the first to go is the reds, the orange, the yellows. Sometimes you get a little green that survives. Sometimes you don't. What survives typically is a blue, which is maybe why the lake looks blue, also reflecting the sky itself. Well, in this particular case, these lights are getting broken up, and the only thing that survives on the horizon is the red and oranges. And those wavelengths is that fellow Raleigh saw scatters least aggressively. So those surviving wavelengths illuminates the sky with oranges, crimson, deep red, pink, gold. And that's why the sun in the midday looks rather yellow instead of white, even at an angle. But Raleigh scatters them, has already moved some of the blue directly from it, and it's shifting towards the warm end then. The geometry of the atmosphere is doing what spectrometers do. It filters out a specific wavelength based on the path. Every sunset is a live demonstration of selective scattering. If we then say, yes, ordinary sunsets are red and orange because the scattering removes the blue, removes the green, now we get these beautiful sunsets at the atmosphere. But here's something that was kind of interesting. In August 27th of 1883, the volcanic island of Krakatoa in Indonesia erupted. It was one of the most violent volcanoes in human history, and the sound was heard nearly 3,000 miles away. The volcano injected billions of tons of sulfur dioxide, fine ash particles, into the upper atmosphere, the stratosphere, above where the rain could wash it out. So as those particles spread over the course of weeks and months, a thin veil of volcanic aerosol materials in the stratosphere drifted around the planet. And everywhere, the sunsets became extraordinary. Observers in London described the western sky, the sunset sky, as turning an intense blood red at sunset. New York, New Haven, other towns in New York State said that the glow on the horizon was so vivid, so orange-red, that the fire engines were dispatched to find out there must be a massive fire out there. There has to be a fire there, and they went looking for the fires. Artists during this time across Europe documented these colors in paintings. A British meteorology made thousands of watercolored sketches of Chelsea's sunset sky for the months that followed that. This volcanic particles was doing something additional to the already red sunlight. It was further scattering, deepening, and all the blue light, all the green light. And so it extended basically the show long after the sun had set. The aerosols, the ash and the sulfuric material in our atmosphere was creating what was called a volcanic purple light. It's a distinctive violet pink visible light in the night western sky at twilight, and that persisted for months. Some reports from that particular period, witnesses said that it was even stranger than that. Sometimes they even had green sunsets. The volcanic aerosols at that point and that specific particle size, the density that was going on, was not only scattering the blue, it was scattering the red wavelengths too, and that left a greenish remainder. So remember, so keep that in mind, that we're not just seeing all the light that exists, we're seeing all the light that can tolerate what it's going through. And so this very unusual condition was only really understood recently. No one really understood why this Krakatoa was creating not only these deep red sunsets, but also these violet and not kind of green sunsets that were there too. Now we understand it. And so then 10 years after Krakatoa in 1893, a Norwegian painter named Edvard Munch, you probably saw his Scream, have you seen the Scream? Anyway, produced one of the most recognizable paintings in the world, which was a figure on a bridge with his hand and cheek beneath waves of orange and red blood sky. And in his diary, Edvard Munch described the moment that inspired it. He was walking with friends when the sun was setting and the sky suddenly turned blood red. And he wrote about this feeling of this unending urge to scream that, because of this. And so many art historians and astronomers now believe that what Munch saw was this decade of unforgettable sunsets, primarily because of the aftermath of Krakatoa. And so the painting we see as the Scream may be in part a spectrometric record of the volcanic eruption on the other side of the world. Isn't that wild? And so the sky tells this story sometimes, and sometimes it just takes a long time to figure out exactly what it is. So let's talk about why dark clouds, when we have a storm, a really severe storm. And like I said, I had 2 tornadoes flying over my house in the last month. Why does the sky get so amazingly dark in the middle of the day? So we're going to kind of take you through this idea. So like I said, we're on a clear day, the clouds are white. And by now you probably understand why that is. Tiny water droplets in the clouds scatter all the wavelengths equally through this process that is called scattering, M-I-E scattering. Equal scatterings of all color produces white. It's the same reason we talked about in the lakes and the ocean that whitecaps are white. The same reason fog looks white, and that's why clouds are white and pillory. It's all those colors getting scattered equally. You get white out of it. So the clouds start building, growing taller and taller and denser, full of more and more water vapor. And as the droplets accumulate and getting pushed around inside of that cloud because the storm is starting to get a little oomph to it, the clouds get thicker and thicker. And the thickness is everything. A thin cloud lets most light pass through it and then scatters back out again. The clouds look bright. They look bright white. And that is because it is more and more of that light then is coming out and scattering. But as the clouds get thicker and thicker, more of the light that's passing through the cloud gets scattered, absorbed, and doesn't make it all the way through the cloud. So then less light is exiting through the bottom of the clouds. And that means that it looks now gray, a gray thick cloud. And as it gets thicker and thicker, it's going to head towards a black cloud because of the extreme thickness of the cloud. When you have towering cumulonimbus clouds, they could reach 40 to 50,000 feet into the atmosphere. So think about that. Clouds are already above the Earth. Airplanes fly somewhere around like 30, 33,000 feet. I've been in airplanes where I see clouds over me while I'm in an airplane because these clouds can go even up to 60,000 feet. And when you get that much water, that much vapor, some of it turning to ice, now almost no light penetrates to the base of the cloud. So the cloud has not changed in any chemical way. It's the same water that was always in the cloud, but what has changed is the thickness of the cloud. And as it grows and grows, less and less light comes through. And so it is called a positional effect. And the position is relative to the sun. And the cloud, how it positions itself matters too. And so if you are standing between the sun and the cloud is between the two of you, it appears bright because you see the cloud, the sun behind the cloud. So when you see a storm cloud approaching in the afternoon, you're looking at the shadow side of it, the undersurface side, because the light is not coming through the cloud anymore. Instead, you can see around it potentially, but you can no longer see the light through the cloud. And the droplets of rain inside of the cloud are growing larger in preparation of rain. It'll start to group together into from fine vapor into actual raindrops, and they become better at absorbing the light and less good at scattering the light. And so the pre-rain cloud full of swelling droplets grows darker even still. And the darkness of that storm cloud is a measurement telling you how much water is inside of that cloud, how much light is being stopped from going through it. See? Pretty cool, huh? So now we're in a severe storm, and we're going to start seeing a very sickly green color coming from the sky. This is the one that stops you cold. Back when I was a kid, I visited my grandparents in Ohio, and we were walking back from my grandmother's house, my cousin and I, and we looked behind us, and there was a sickening green sky. And if you've ever seen it, you know exactly what it means. It means a tornado's coming. It means you're in trouble. And like I said, if you've ever seen it, you will remember it for the rest of your life. It's not a subtle tint. It is really an unsettling green cast in the light itself. And it makes the whole landscape look science fiction. Everything looks wrong. The shadows feel wrong. And you, like I said, you get this feeling in the air. The storm chasers describe it, and tornado survivors describe it. The people who have never even heard of this Raleigh fellow and his Raleigh scattering, they know exactly what it means when the sky turns this color. But what causes it? The honest answer is, and scientists know in general why it happens, but the exact mechanism is still being debated. NOAA acknowledges that there's not settled consensus on it, essentially, but essentially what the idea is, that it's a complex optic of the atmosphere at that particular condition. And the main leading explanation of all of this is interesting. So a severe thunderstorm, supercells, right? capable of producing large hail, tornadoes. That's what I had by my house. They reach 60,000 feet, contain a massive amount of water and ice, and they have reached their peak intensity, usually in the late afternoon, early evenings, and the air has had all day to warm, right? So the sun has been beating down on the ground all day long, and now you have this dark cloud full of water and ice. And then because the late afternoon sunlight is already reddish, right? We talked about the sunset is going through more of the atmosphere and turning it red. The sun is dropped into the lower sky, so we're getting most of the blues filtered out of it. What is happening now is that this orange and red is would have been there had we been looking at a sunset. Now you add the storm cloud, and inside this deep water-laden thunderstorm, blue waves are scattered. The interior of the cloud grows blue from all the scattering. The base of the cloud is appearing to be very dark gray from the internal scattering of there. And so this blue that is inside the clouds itself, illuminated by the reddish afternoon light, and suddenly when you mix them together, you get some sort of a reddish ambient producing greenish cast, essentially. That's what the big theory is. And it's not because of green in the atmosphere or that, like I said, anything chemical has changed. There's no frogs or grasshoppers getting blown up into the tornadoes. That's used to be what people thought were happening. But instead, you're basically seeing two different pools of light mixing together. The red of late afternoon or sunset, and the blue scattered by the enormous column of water inside the clouds. And so researchers point to this role of hail, too, that hail itself has different optical properties than liquid water. The ice crystals prefer to absorb red wavelengths, scatter blue-green wavelengths, and so if a storm is producing a huge amount of hail, it will intensify that green effect. So the green sky is not a guarantee of tornadoes, but it does mean that there is gray and black coming from the storm itself. The green skies can indicate that the storm is severe enough to produce a lot of hail. And oftentimes when you get a lot of hail, you may also get tornadoes. So the green sky is reliably an indication of very moist-laden storm clouds, the kind that are supercells that are capable of producing large hail, violent winds, and sometimes tornadoes, and being intensified by the storm itself, but then also reflecting that red light. So this is really what matters, is that if you see that particular green sky, it doesn't matter why this or what's going to happen in this storm. It is telling you that light is passing through something extraordinary, and it's a warning. If you, like I said, if you see that sky, you take cover. We can see why that green sky would get a lot of attention if you've ever seen that. And there's other types of colors that storms can produce. So sometimes there is this sort of a teal blue-green right before hail. Before there's large hail, the sky takes on, inside the storm itself, like I said, this sort of teal color. And sometimes people call it like a sickly yellow-green. I think it's actually a really pretty green. And so this tends to occur when there's less of the late afternoon red component. Think more like the midday storms or the storms where the angle is different. There's large particles of ice inside of the storm itself. It's absorbing the red wavelengths, leaving you with a blue-green color to scatter back to you. With less red light mixing in, it produces really this classic greenish blue color that's closer to teal. And it's still a sign of deep intensity inside of the storm itself, but certainly a cooler tone of it. And sometimes you might even see sort of a deep purple, or they call it a bruised violet sky, that indicates a very high water content in the storm that's approaching at dusk time or shortly after sunset. And this is basically with the last remaining ambient light, which is shifted towards red, and even the red light is getting absorbed into that. The same principle is that the lower light levels are shifting red to create this ambient illumination, and then the blue of the storm that's inside the storm itself, because it's scattering the particles with all the water and ice inside of it, and what remains comes out is almost like a purple, a very deep purple, and that's also very unsettling. Storm observers have described this one as probably the most alarming sky colors of all, partly because the lower light suggests that the storm has blocked out a large portion of the sky above, and it's disturbing. I have never seen that particular color. I've seen the sickly green, but never have seen this purple business. I've also seen the teal that was there. And then comes sort of a greenish black, and this is the most extreme version of it. When a tornado survivor talks about the alarming sky, they talk about a greenish black instead of the greenish yellow sickly color. The green casts a deep storm, essentially, and that darkening, because the storm is blocking out most of the available light. So it's almost like it's night outside, even though it's not nighttime. And then you sort of get a green sky in the overcast of itself. And like I said, everything just looks wrong. So it shifts in color, and the storm's intensity, the thickness of the cloud, how the light is reaching you, and it creates that situation. So you can see right now that essentially the sky is a giant spectrometer. It's telling you about what is going on in the sky overhead or off into the distance based on the color that you're seeing from it. And you can get a lot of different colors, throughout that. Some other types of spectrometry you've probably seen. There is something called crepuscular rays, which is also known as God's rays. Those are those really radiant beams of golden light. Then sometimes they come out at sunset. Sometimes it's a shaft of golden light in a gap of clouds. Have you ever done that? Have you ever seen that? There have been times I've been driving out in the countryside, and it's kind of a cloudy day, and suddenly this glorious beam of light is just raining down. And like I said, it looks golden. It's beautiful. And I've seen that before. And essentially, this is coming from light that is coming through a single opening in the cloud itself. The rays are parallel, and the sunlight travels in parallel lines. And so the sun is so far away that essentially these parallel lines that are reaching us, it's giving this perspective that it's converging at a single point, that the light is just coming in at this single point, but it is essentially because the clouds are filtering out the light in the other places, and in this gap of clouds, it is essentially pointing in a certain direction. They are, like I said, we think of, I think, sunlight as being one of those things that's spread out, but rays aren't spreading out from the sun because the sun is so far away. They are parallel. Our visual system interprets parallel lights as extending far away. It looks to us like it's converging at a point just because of how our eyes interpret it. But the beams themselves are visible because the particles in the atmosphere, the dust and the humidity and the droplets of water that's around, scatters the light sideways so that you see the path that it's taking perfectly. It's this perfectly clean air lines that you're seeing. And because if it hadn't been for this particular perfect air that you see right here, you wouldn't see the light or the beams of light the way you do. If there had been haze around, it probably would have scattered the light a bit more. But because of these, what they call anti-crepuscular rays are coming in that same phenomenon in the opposite side of the sky, the same parallel rays now converge at this point, and the point is directly at the opposite, it's from the sun to that point, and it looks like they're rushing together at the horizon. And what you're watching is it diverge to a point. There was a poet named Gerard Manley Hopkins who is the same guy who would later write about Krakatoa's sunsets. He published his first scientific writings about this in 1882, and he described them with this precision of a charged blue sky above, the light lowers through these clouds is sweet and below. So essentially, you're just getting this very pure form of light because of just the nature of the clouds, the nature of the sky at that moment, and then your perspective as looking upon it. Think about rainbows too. When you have a rainbow, that's a full spectrometer right there built from raindrops. So when light enters a raindrop, it refracts, it bends around the surfaces, and different wavelengths bend in different amounts. The light then reflects off of the back of the surface of the drop and refracts again as it exits. And so as a result, this white sunlight has been spread into all its component wavelengths by basically the droplets of water in the sky. Red exits at a slightly shallow angle, so you'll see the red arc on the outside of the rainbow. The violet exits at a steeper angle, so then you'll see it on the inside, and each color has its own radius arc, separated by unique refractive index of water. I don't want to use big science for terms here, but essentially, as these light waves are bouncing off the water, they each have their own position based on how they come out of this. And so then you will see a rainbow appear. Sometimes you might even see a second rainbow appear that might be fainter, have a wider arc than you see outside the main rainbow that you see. So it forms from light bouncing twice inside of a droplet. And so that second bounce reverses the order of the colors, and you'll sometimes see a secondary rainbow inside of that. It's very fascinating. There's even sometimes what they call a darker band, which has been called Alexander's dark band because there's almost no light exiting from the drops at all at that particular angle. So every rainbow is, again, another spectral composition of the sunlight or decomposition. The sunlight's hitting it and bending out into a million different individual water droplets, all doing the same kind of refraction simultaneously, and each one of them sending a different wavelength to your eye at exactly the right angle. I don't know if you've ever been to Hawaii, but one of the things that's most remarkable about Hawaii is it seems like at every given moment, there's a rainbow. And then there's a rainbow inside of a rainbow. And then there might be even another rainbow. And at one point, too, I was able to see an area where it looked like a rainbow ended. And that all has to do with the geometry of raindrops as the sun is broken up inside of it. Sometimes you might even see something that's called a green flash, and I've not seen this myself, but at the exact moment the top edge of the sun disappears below the horizon, under atmospheric conditions, a bright, vivid green flash can appear. And this is caused by atmospheric refraction, same principle as what we got with the rainbow. The bending light from the sun, so we see it as it passes over the horizon. The different wavelengths are refracting in different amounts of different wavelengths, and the red light refracts the least, the green and blue refracts the most, and as the sun sets, the red position just disappears, the blue scatters away, and what's left is the green. So you suddenly get a quick flash of green, and that was the last piece just as the sun goes below the horizon. So the green flash is real. I heard people think that it was a myth or an optical illusion. My friend and I, when we had to work in Hawaii. I know we had to. We had to work in January, February, and March in Hawaii. We hoped, to be able to see that green crack at the sun set over the oceans. And so we did look for it. I thought I saw it once, and then I think I was just not sure that it actually happened. But essentially, it just lasts 1 or 2 seconds under ideal conditions. Low humidity, clean marine horizon, stable air. And so sailors have documented it for centuries. Jules Verne wrote about it in 1882. Boy, that 1880s was a big time when Hopkins wrote about his information. But it's basically very rare. It's a brief gift, essentially from atmospheric optics. You see it, and then it's gone. And it's just one of those things I think you have to witness for yourself. Boy, I hope you've enjoyed this whole series talking about color and the analysis of light as not only just a scientific instrument, but something that we can see in our day-to-day lives. I don't want to get this podcast and this YouTube channel to be too scientific-y. I just want, you to be able to understand what you see out there when you're looking at different things. We've talked about everything from fires to ponds and lakes to planets and stars, and now towards the weather. When you look at the color of things around you, whether it's birds, blue jays that are just absorbing color differently than when it's gray outside or whether it's blue outside, or a cardinal that actually has red feathers, the world around us is full of colors. And sometimes there are reasons because that is what color it is, like the cardinal, or sometimes it's because of the geometry that is happening, or sometimes because of the atmosphere and the molecules that are happening to it. And it just absorbs differently. And so when you see a color, I think now you can kind of ask yourself the question, am I seeing that cloud over there as green because of what's going on inside of that cloud? Yes. Is that cardinal red? Yes. Is that blue jay blue? No. And you might understand a little bit more over the course of these 4 episodes about why you're seeing color the way you are. And let me tell you, there's a lot of information out there on the internet. So if you don't understand something, or I went through something too quickly, I hope you at least have the vocabulary to be able to look up what it is you're looking at and say, hey, why is that cloud green? Why is that bird blue? Why is that fireplace red? And we'll know a little bit more. This is something that is happening everywhere, all the time. And I just hope that you will have a bigger appreciation for the colors you see around yourself, and then start asking yourself the question, why is this color the way it is? All right, everyone, thanks so much. I appreciate you going through this series with me. I hope you've enjoyed it. Spectrometry is just one of my favorite things. When I learned about it as a kid, I was obsessed with it. You can find everything I do at jillfromthenorthwoods.com. When it comes to YouTube channels, podcasts, I do all of my work in both podcasting and YouTube. So I hope you listen. You can email me at jill@startwithsmallsteps.com. I appreciate you being out there.